Hello, welcome to Module 1, Lesson 7 of our COSP Plus course. On this lesson, we're going to cover the following, such as cryptography and PKI. So, DID, right, or defense in depth, is a method for securing corporate networks. Defense in depth includes safeguarding data in all three of its life cycle stages, like in memory, in transit, and in use. To maintain data confidentiality, we can encrypt it using a variety of methods. We need to be able to use hashing and signing to check the data's integrity in some situation. It can be difficult for IT professionals to grasp the complexity of our cryptography, which relies on mathematical ciphers. IT professionals and management have the responsibility to ensure that the proper standards and protocols are enabled by asking the right questions. The use of cryptographic ciphers to protect data stored, processed, and transmitted by an enterprise may be subject to stringent regulatory requirement. It is the responsibility of security professionals to ensure that the appropriate technology is configured and deployed. So the first topic is a hashing algorithm. Data integrity validation is the primary use of hashing algorithms, but they can also be used to prove that you know a secret, right? Such as a password. Password A hash cannot be reversed and does not provide data confidentiality. Hashing is actually a one-way process. That the original data has not been altered in any way is critical. Hashing is the process of creating a unique digital checksum for each document, file, or data payload that is sent over the internet. If a protected operating system file has been altered, we can use hashing, right, to find about it, right, or FIM, the file integrity monitoring. In digital forensics, a copy images checksum can be hashed to create a unique checksum that can be compared to the original, right? And this is useful to do before analysts begin the forensic investigation. For security professionals, it is critical to know the difference between strong and weak hashing algorithms. So there's actually three, right? The first one is SHA, or the secure hashing algorithm. Most businesses and government agencies adhere to the SHA standard. In cryptography, the SHA-1 hash function produces a 40-byte output with a fixed key length of 160 bits or characters. When most cryptographic packages stopped supporting SHA-1 around 2010, it was considered obsolete. SHA covers the following hash functions like SHA-224, 256, 384, and 512. Next one is HMAC, or hash-based message authentication code. An authentication and integrity check can be performed on a packet using HMAC. A hash function and a secret key known only to the sender and the recipient will be used. An HMAC can be generated and verified on the receiving host. It is important to note that an HMAC does not encrypt the payload, instead it authenticates the packets. For non-repudiation, you need a digital signature, and this does not. Third one is MD, or the message digest. Ronald Rivest developed the MD2 hash function in 1989, which was originally published as MD2. MD5 was the culmination of a series of updates. It was widely used up until about 2008 before it fell out of favor. Hash collisions are now included in the list of possible exploits, and this happens when two distinct inputs provide the same hash value. Like, for example, an attacker could replace a legitimate document with a modified version that has the same output hash. Now let's talk about symmetric encryption algorithms. Symmetric encryption gives privacy by encrypting large amounts of data at once. It is very good at encrypting both data at rest and data that is moving. Because the key sizes are not too big, it is very fast, right, compared to asymmetric encryption. Symmetric encryption uses the same key to lock and unlock the data. The block ciphers and stream ciphers are two main types of symmetric algorithms. So for block ciphers, right, with this kind of ciphers, data is encrypted in 64-bit or 128-bit blocks. Stream ciphers are faster, but they don't offer the same level of security as block ciphers. So what are the types of block ciphers? So we have 3DES. We also have AES. Okay, there you go. Now, what about stream ciphers? Stream ciphers works best for traffic that happens in real time. They are fast and they make fewer mistakes because they handle data as stream of bits. RC4 used to be the standard for stream ciphers, but it is no longer thought to be safe and has been taken out from widespread use since 2015. The well-known stream ciphers of the 21st centuries are ChaCha, so CHA, CHA, Salsa 20, and Salsa 20. Okay, there, too. Now let's talk about asymmetric encryption algorithms. Asymmetric encryption is designed to support secure key exchange and agreement, as well as non-repudiation through digital signature. It is not used to encrypt large amounts of data because compared to symmetric encryption, the key sizes are just too big. This would mean that encrypting a lot of data could take thousands of times longer. Now, in asymmetric encryption, there is a public key and a private key that are related mathematically. The public key is like your bank account, right? That you can give to a customer who wants to make a payment. Then your private key is used to get to your money in a safe way. In this case, the private key could be your bank card, the PIN, or the CVC code, right? And you wouldn't give anyone your private key, okay? So there's a couple of types of asymmetric encryption algorithms. The first one is RSA, the Revest, Shamir, and Adelman. RSA is used to exchange keys and make digital signatures in a safe way. It was made and published in the 70s and making it one of the oldest asymmetric algorithms. It comprises of a public key and a private key that are related mathematically. You can share your public key, but you must protect your private key. The typical size of an RSA key is between 2048 and for 4096 bits, but more stringent security standards call for keys within the 3072 bits. Next is the DSA, or the digital signature algorithm. So DSA is a standard for digital signatures set by the government. Digital signatures are used to prove that you are the owner of a document when you send it by email or to verify a certificate that is hosted on a website. Third is DH, or Diffie-Hellman. DH is a protocol for agreeing on a key that is usually used to trade a secret or session key for IPsec or SSL TLS. It's not used to trade keys, but it does let two people make their own secret session keys. This is helpful because it means that the session key was never sent, and this means that any MITM attack would fail. ECC, or the elliptic curve cryptography. So using algebraic equations to draw an ellipse, ECC makes it possible to make key pairs. Keys can be made by putting points on this ellipse, and this is a simple description of a complex mathematical process. The key agreements and digital signatures both use ECC. ECC's strength is that it works well with low-power devices. With ECC, a key size of 256 bits is the same as a key size of about 2048 bits with RSA. All right, let's now talk about encryption protocols. So hashing, symmetric encryption, and asymmetric encryption are all building blocks that help applications and protocols that need to store and send data securely. Using the strengths of different types of encryption, a cipher suite is used in many processes, right? And we rely on these protocols to keep users safe when they use online banking or work from home. They also keep information systems safe when they need to be managed across the network and make sure the emails sent and received can be trusted. So in the next few slides, we'll look at some of these common protocols. First is SSL TLS, right? And it's used to encrypt many application layer protocols like HTTP, SMTP, IMAP, LDAP, and many more. It gives privacy, right, through encryption, and reliability through HMAC. It uses a set of protocols that make use of a hybrid cryptography. As you may know, SSL isn't used anymore because it isn't safe. However, TLS 1.2 and TLS 1.3 are now the standards. Next is S/MIME, right? This is the standard for email and lets people use the same protocol. This lets users choose an email client so the enterprise can run an SMTP server from any vendor. We can protect emails from one inbox to the next by encrypting the payload with the public key of the recipient and the session key. The message can be read by anyone who has the recipient's private key. Next is IPsec, right? So for VPN or virtual private networks, IPsec is a mechanism for encrypting data in transit. Site-to-site links can be protected with this, as can mobile users access to the corporate network. Hashing, such as HMAC, will be used for bulk encryption, while symmetric and asymmetric encryption will be used for secure key exchange. Next is SSH. SSH is a secure shell for administering servers and equipment. As a result, SSH uses a type of encryption known as hybrid encryption. PuTTY is a popular tool for securely connecting to a remote computer. In order to connect to an SSH server, PuTTY must be configured, right? PuTTY must be configured. Next is password salting. A password can be protected against offline attacks using tables and brute force techniques by using this method. It is possible to generate a pseudo-random sequence of characters when the password string and salt are hashed together, and the salt is added in. All right, now let's talk about PKI, specifically PKI hierarchy. So PKI, or public key infrastructure, is very important for any company size. PKI gives an organization the tools it needs to check the keys that will be used to secure the data and prove who they are. So without PKI, we cannot use encryption keys because we can't be sure that the keys are real. When the key pair is made, we need to give the unique public key a trustworthy certificate that has been signed, just like a passport is made for a trustworthy citizen. Without PKI, we can be sure that we can use online banking, e-commerce, smart cards, or virtual private networks. It is important to know how the whole process works and where the problems might arise that may need to be dealt with using problem-solving skills. So what's a certificate authority? A CA, or a certificate authority, is made up of an application server that runs a service called certificate services, which is like just like a daemon on Linux or Unix. So CAs can have more than one level, but there will always be a root CA. Most of the time, there will be at least one more layer. This is called the intermediate or subordinate CA. Most of the time, the root CA will be kept in a safe place, often by itself or air-gapped, and the root CA only needs to be turned on and ready to sign requests from intermediate CAs. For safety, a business may have more than one issuing CA. The issuing CA must be powered on and ready to sign the client CSR, and it will need to be highly available. A standard is used to make certificates, right? And the current standard is the X509.v3, which says how a digital certificate should look and what information it should have. Okay, that's the CA, the certificate authority. Next is a registration authority. So when a request comes in from a client entity, it is checked against policies to see if it will be approved. Verification checks must be done before a certificate that verifies a domain name or other identities can be given out. The registration authority's job is similar to that of an auditor. So if you wanted to get a passport, you would have to prove who you are. If you didn't, someone could steal your identity. In the PKI hierarchy, the passport would be the digital certificate and the RA would be the government agency or department that issues the passports. Next is the certification revocation list, or CRL, right? It refers to a list of certificates that should no longer be used for or trusted. It is made public by the CA, or the Certificate Authority. If a certificate is given a 1-year expiration date and a key is stolen during that time, the CA can revoke the certificate and put the status on the list that anyone can see. Certificates can be taken away for a number of reasons, such as the end of a business, a change in affiliation, or the loss of a key, and there are more options here. Next is what we call as OCSP, or the Online Certificate Standard Protocol, and it has become the standard way to respond quickly to a client's request for revoked certificates. This is so that clients can get answer faster. If a client only has a CRL, it needs to connect to the CA CRL server and get the most recent CRL entries. If the CRL network isn't available or if it goes down for a short time, a client can check the status of a public key certificate. With OCSP, however, the OCSP service can cache results and answer clients' requests even when the CRL is temporarily offline. The OCSP is also much easier to use because it only needs to check the serial number of the public key certificate. Once the PKI hierarchy is set up, we will need to give certificates for many different purposes. Okay, here's the last lesson here, right? We're going to talk about certificates. So when signing up for certificates, large businesses have very specific needs. Sometimes the goal is to make it easy to manage or to be able to add more sites to an e-commerce operation. Customers may sometimes need a peace of mind that comes with highly trusted certificates. Here are a few types of certificates that are often used. Wildcard certificate, right? So with this, an organization can use a single pair to host multiple websites with a single certificate. Depending on how many sites you host, there may be restrictions or extra cost. All of the sites here, or all of the sites that the wildcard certificate covers, must use the same DNS or domain name, right? Only the host name can be different for each site. Next is extended validation. An extended validation certificate is a type of certificate that gives a high level of assurance. It is mostly used by banks and other financial institutions. Customers will be able to tell that a site has an extended validation certificate by looking for a sign on their web browser. Sites that sign up for extended validation certificates get extra security services and help from the CA, like vulnerability scans. Next is a multi-domain. A multi-domain certificate is right for an organization that needs to support more than one domain within a single certificate, or with a single certificate. This certificate is different from a wildcard certificate because it lets a site have multiple subdomains, domains, and host names. Next are general purpose certificates. So here, a user could be given a certificate that could be used more than one case. A user may need to sign and encrypt email, log into their AD or Active Directory Services account, and use secure VPN access. We could cut down on administrative work by giving each user a single certificate. And the last one is the certificate usage and templates. So it is important to make sure that the CA has the right templates enabled so that the user request can be met for all the applications that are being used or planned. The following are common types of templates like client authentication, server authentication, digital signatures, code signing, and general purpose. Okay? All right. That's the end of the lesson. Here we spoke about cryptography. We spoke about hashing algorithms, encryption algorithms, encryption protocol. And we also spoke about PKI, public key infrastructure, covering PKI hierarchy and certificates. Okay? Thank you very much for watching the video.